Okay, so our project is about digital stethoscope with noise suppression using FPGA amplifier filter. So we can see in the FPGA board we have a mic input, which is a very tiny little port. This is where we are actually giving the heartbeat sound from the stethoscope. And these are output port, which is an audio jack, a 3.5 mm jack. And we will hear it in our main, we should hear it in our main speaker, but in the phone we can't capture it. So that's why I would actually show that in a demo. So now we are actually giving the input from the heart using an stethoscope, we can see. And we are hearing the heartbeat sound pretty.
So here's our code part. So in the code part, if you want to summarize the whole things, we can divide it into 6 sections. So these are the 6 sections at a glance. So now let's go to the code and explain in brief what's happening here. So at first we defined our parameters and everything, and then we dealt with our 100 megahertz clock inbuilt in the FPGA board that we're using. But we cannot work with this 100 megahertz clock. Whatever the filters or filtering we do or capture the audio, it is not enough. So we have to reduce the frequency, and we already know from the theory the frequency division method. So by that we reduce the frequency at 2.4 megahertz. And let me explain the thing that what's happening in the mic. So the mic that is inbuilt in that particular FPGA board, that mic data is always comes inside the board as a PDM data. PDM means pulse density modulation, which is nothing but a stream of ones and zeros. Then when the amplitude is very high, it's just ones. The amplitude is very low, just zeros. But dealing with PDM signed PDM or PDM beats is not ideal, because if we just directly deal with the PDM and we want to filter it out, then there's always a DC offset. That means there'll always be a very high pitch sound or gain. So as a result, the filtered audio will always have a hitching, a very high pitched sound, which is not desirable, because we want to capture the heartbeat and we want to suppress all the high frequency components as much as possible. So we don't want this, and that's why we need to convert it into a sine beats now. So this is the section where we actually convert it into the sine beats. This is the section. That means the PDM data from the mic that is coming here, the real-time audio, the PDM data, those have been converted into this particular sine beats here by this particular line. And then we pass through the whole signal through a CIC filter. So CIC filter is basically used for better filtering out the signal, because the data is coming from the PDM. It's not enough. And because whatever the PDM data we have, even though we convert it into a stream of ones and minus ones, but if you want to do the signal price and everything, we know that we have to do the PCM or pulse code modulation. So CIC filter is a way to convert it into a PCM that is called the decimation. So the decimation factor that we used here is about 64. And so the beats that we're getting here, that means we are getting a 16 beats PCM signal by the CIC filter, and we used a third order CIC filter here. So after the CIC filter, the PCM signal, this must be filtered out. That means we just convert it into a signal. So we convert it into a desirable or desirable signals that we want to do the filter, or that we want to do the filtering. So for the filtering part, we used a Kaiser window and 32 taps to just accumulate at the MATLAB, in the MATLAB, to determine the coefficients. And after determining the coefficients, these are the coefficients I found from the MATLAB. We multiplied the sample by the particular coefficients, and got our filtered output. So these coefficients has been derived very carefully by determining the sampling frequency and everything from the MATLAB code, and we'll show that later on our video. And after the FR filter or the signal is filtered out, then the whole signal or PCM signals is passed to the PWM, our last section, the PWM output. That means the signals, that is the PCM, the pulse code modulated signal, that to hear the audio at the audio jack output, we must need to convert it into a pulse width modulated signal. For that, we converted the 16-bit PCM signal into a 10-bit signal. So these 10 bits should be carefully filtered, or should be carefully chosen from the PCM 16-bit signal. So these 16 bits, from the 16 bits, for better intensity, and by tuning the sound properly, by tuning or hearing the sound from the stethoscope and everything, we came to a conclusion that these are the best signal that we can get, or the best beats that we can choose for the audio here. And then after that, we simply just pass it through our main audio jack output, and through a headphone or the video. It is already shown here that the heartbeat can be sound or can be heard. And now the question here is that at the PWM, the output here is basically a 97.6 kilohertz output, which is basically unsigned beats also, because in real time we cannot work with the signed beats. But so how can we hear the sound at the audio output now? So the problem here is not that difficult, because in the audio jack output there's a built-in filter here. So that built-in filter can automatically filters out that audio PWM signal that we're passing through, and then we can hear the clean heartbeat sound that we had already shown earlier. Now